Hi, everyone. Thank you for joining us today. My name is Edwin Robledo. I'm part of the support and tech marketing team for specialists for Fusion 360 as well as for Autodesk Eagle. And our presenter today will be Jorge. And we'll be beginning in approximately 4 minutes. We'll be starting. Thank you.
So hello everyone, as we wind down to get started with today's live stream, just want to let you know that every day during the week, the Fusion 360 organization has different live streams going on with different team members covering some of the main topics in Fusion 360. So if any of these interest you, definitely keep an eye out for the live streams. We're doing them every week on the days as shown in the schedule here. So we'll be getting started shortly.
I've been able to see some of the ones made by Brad. They're actually very nice. Brad does a really good job, very detailed.
I don't know what happened with my counter, but it's stuck at 216. So
No worries. It's about right. As you join us, always appreciate to know where you're from. If you don't mind just indicating where you are joining us from, would greatly appreciate it. Jorge, just to let you know, we've lost your screen.
yeah, got stuck for a second. Give me 1 second. All right, Ed, sharing the screen. Let me know if you guys can see it. Can everyone see it, Ed? Check, check. 1, 2, 1, 2.
Hi, Jorge. Sorry about that. I was looking for the unmute button. I apologize for that.
No.
Yeah, your screen seems to be working just fine, Jorge. Thank you.
Excellent. Okay. So let's go ahead and get started with what we are planning for today's video on SPICE simulation. Now, most of you maybe watching this live stream are from a mechanical background, so the concept of simulation is not alien to you at all. You're familiar with the idea of a thermal simulation, load simulations, things like that. So in electronics, simulation fulfills a similar role. It's basically the idea is to verify the integrity of design before you commit to manufacturing it. And obviously being able to do so quickly and cheaply speeds up the design cycle and also minimizes the need to respin your designs. So it's in your best interest to learn to have an idea of what SPICE simulation is and what it does. So SPICE is an acronym. It basically stands for Simulation Program with Integrated Circuit Emphasis. Okay, so the idea is that by setting up a netlist, the program runs through it, does the math, and gives you the waveforms for each of the nodes. It was originally developed by Berkeley, and every SPICE or circuit simulator you'll run into today is for the most part a derivative of the work that was done in Berkeley. So everything has kind of built on that engine. That engine over time has matured, and everyone's just kind of put their own GUI on top of it. It's very mature, it's well understood. The differences you're going to see in usability are pretty much exclusively due to the interface implementations of those who build on top of that SPICE engine. So in this webinar, the goal is to show you how to work with the SPICE engine inside Fusion 360 Electronics, show you the key things you need to keep in mind when assigning your models and setting up your simulation parameters, as well as the different types of simulations that are available to you. And then we're going to go into some advanced examples. And the idea is just to give you a taste of what's possible. If you know what's available to you, then you can see how to apply it to your specific circumstances. So right now I have this schematic. This is a very simple example. And the idea is that it comes in with no SPICE association at all. And what we're going to do in the first part of this webinar is basically do the association. So what I'm going to do right now is I'm going to close my control panel. That way it's not in the way. Okay. And what we can do is a really nice way to do it, especially in a circuit this one, is you can just select everything. And then you can right click and select add model. And it'll come up with this message letting you know that the ground symbols, because of their named ground, the engine is intelligent enough to know that you probably want this to be a node 0 in the SPICE net list. So we can say yes or no, etc. But actually, before we do this, I want to show you something. How do you know that you don't have things modeled? Well, if you go here and you try to set up a simulation, first thing it's going to do is let you know unmapped models have been found. All components must be mapped in order to be able to simulate. So what we're going to do is, again, we have the selection. I right click, add model. Want to convert? I'm going to say yes. When I do this, you're going to see that these should already be mapped, but it seems like it had a little issue here because it did specify them as ground, but the warning signs didn't change. Okay, but they are correct, and they should be correct. These did not, though. So let's go ahead and adjust these. So actually what I'm going to do is I'm going to probably switch this to something else and then put it back to ground power pin, yeah, and that'll update it. Okay, there we go, ground power pin, perfect. So now these, if you notice, the program takes a guess at what the different parts are. R1 is a resistor, so that was a correct guess. LED1 is not an inductor, so we're going to switch that to a diode. And then G1, which is the battery in this case, we're going to change that to a voltage source. Okay, an independent voltage source. Now, if you notice, SPICE defines certain cookie cutter type components. And that's what you see in these dialogues. It basically shows you those cookie cutter type components that you can pick from. If you have something that's maybe a collection of these components or more involved, in those situations, you'll pick subcircuit. And then when you go to map, you'll have to import a model. Okay, for this simple demonstration today, we won't have anything that uses a subcircuit. But if you're working with integrated circuits, op amps, digital logic, etc., you're more than likely going to be working with subcircuits. Okay? But for this example, we can just say independent voltage source. So right now, we have these three components where we've selected the SPICE type, but they're not mapped. So we're going to select map. And because it's an intrinsic model, that's what it's called, and you'll see it in the load model. It's hard to see because there's little contrast here, but it says intrinsic device, no model. Intrinsic devices are, like I mentioned, those cookie cutter, those built-in models that SPICE understands as a base model. So those you don't have to do anything special with. So here with the resistor, as we know, resistors work however you plug them in, so it's not really critical that I change this, but just for semantics, let's match symbol pin 2 to model pin 2 and symbol pin 1 to model input 1. So I'll say OK. You'll see we get the check mark, so it's happy. Now for the diode, we can do the same thing. We'll select map. Now in this case, even though it is an intrinsic model, there are many different types of diodes. And SPICE allows you to kind of specify some very, very detailed parameters about the diode. So you can put in temperature coefficients, you can put in different PN junction parameters. There's a lot of specificity that can go into these models. Most of the time, you don't want to make a SPICE model from scratch. You're better off using an existing model or a model provided by the manufacturer of the component. Now, manufacturers are going to be very interested in giving you good models because that guarantees or helps you as an engineer to use their components. So your best bet is always, if there's a manufacturer supplied model, to use it. It's a very important point. If not, you can try Googling. You'll usually maybe find something like a university has made for their students, something like that will usually work. Okay? It's important when you get one of these models that you read. The models will usually carry some documentation about the assumptions made in the model. You want to read them, especially if you have a very sophisticated application. You want to make sure that your model is going to be able to simulate the aspects that you're interested in. Okay? Because again, the quality of your result is directly linked to the quality of the model you use. If you use a bad model, your results will be worthless. So in this case, for this circuit, I'm going to use one of the built-in diode models. Okay, and I can grab it from multiple places, but I find it easiest to just grab it from Eagle for my application. So I'm going to go over here. I'll go to examples, SPICE, examples. I'm just going to grab this D mod here. Say open.
I would just like to remind everybody that if you do have a Fusion 360 subscription, Eagle is included for free. So you could download and
Mm-hmm.
have all these resources from Eagle available to you as well.
Correct. With that said, the model is included in Fusion as well. It's just a bit more folder divey. In order to find it, you have to go through more directories. And I knew where this one was off the top of my head in Eagle, so I went with that. So I'll click OK. It's going to say model file found. Do you want to overwrite it? I didn't change it. So in this case, I can say yes. Verified. Yep, we say OK. And you see cathode, anode. The anode is where the positive input should be. Cathode is where the negative input should be. I'll say OK. This one is now mapped. Independent voltage source. This one's an intrinsic, so this one is going to go straight to mapping the pins. Make sure positive is positive, negative is negative. We say OK. So at this point, all of the components in our simulation have been modeled. So we can say done. And we have this here. Now, one thing that's good to know is In this case, the components do have PCB packages associated with them. But if you look in the ngSpice simulation libraries that ship with Fusion Electronics, you'll see that those actually don't have any footprints associated with them. They don't need to, so they won't contribute anything to the board. So if you're going to use straight from the simulation library, then just know that they're not going to add anything to your board. If you already have your design laid out and you have your schematic, then what you can usually do is just by assigning models to the components that are already on the schematic, you'll be able to use the same schematic to define both your layout and to do the simulation. So you kind of don't have to do any additional work there. Okay, so everything here has been modeled. We do need to specify a value for this resistor because otherwise Spice won't know what to do with it. So I'll click here on value. That's one way to do it. Put 220. Another way you could do it is if you click on the part, sorry, with no command active, then you'll see that in the inspector it shows up and you can change the value here. So there's multiple ways to do it. Everybody finds a way they prefer to flow with it. And then here, remember that we turned this into an independent voltage source. So this value doesn't help us at all for the independent voltage source. So I'm going to right click and you'll see that you have the option to do an analog source setup. I'm going to go ahead and select that. DC value, let's just say 0. I don't want it to have any DC value. I want it to have a sinusoidal transient function. So basically this is going to output a sinusoid stimulus into the circuit. Offset, I'm going to offset it by 1 volt. I want its amplitude to be 1 volt. I'll put here 1 kilohertz, or just 1K is fine because it already knows it's kilohertz, even though I can put it in. I'll hit set value, and you'll see that now this string is meaningful to the Spice engine. Okay, so what we're going to do now is I'm actually going to put a couple of probes so that way we plot this when we run the simulation. So what I want to do first is actually change the name of these nets. So I'm going to click this. I'm going to change the name to be VN. That way it's something meaningful. I'll get this one. I'll change it to be V out. Okay, perfect. Okay, nice. And we're going to put probes. So you can put a voltage probe, a phase probe, and if you look in the ngSpice simulation library, you can also put in a current probe. But for our purposes, we just need a voltage probe. I will probe this net right here and this net right here. All right, we'll say okay. That's it. Now we're ready to set up our simulation. So we're going to click here on the simulate button. Now you'll notice there are several options here. Okay. Operating point is the simplest of all the simulations. What it will do is at DC, in other words, there's no transient behavior whatsoever. It will calculate the voltages at all the nodes. And it will also calculate the current through any independent sources. So typically when students run into circuits 1 classes, typically this is what they're doing. They're calculating the circuit's operating point. DC sweep will allow you to select a parameter and vary it and see then how the circuit responds. So DC sweep basically builds on operating point by running the operating point simulation multiple times at each of the sweep values. With AC sweep, we now start to get into more sophisticated analysis. AC sweep will basically put in a sinusoidal waveform and it will sweep it across a range of frequencies that you specify. And this is really useful when analyzing filters, audio circuitry, anything that has any type of frequency dependent behavior, you can analyze using an AC sweep. And then finally, we have a transient simulation. So whereas an AC sweep works in the frequency domain, a transient simulation is working in time domain. It's actually seeing how the circuit develops in response to a stimulus over time. So if you notice here in the transient, we have the number of points. So basically in whatever range we put, it's basically going to split it up into those points. If it notices an area where the behavior is changing quickly, it will add in more points. That's why we have a maximum number of points here. And the idea of that is to improve resolution whenever you have a lot of changes in a certain range of time. Temperature is used whenever you have the circuit temperature coefficients. So for example, if you're doing anything like auto or aerospace, your circuits are going to be subjected to different temperature ranges. So 25 is something that you could consider maybe a little bit above room temperature. Okay, sometimes some people consider room temperature 20 degrees C, others pick 25. Either one is okay 90% of the time. If you're dealing with circuits that are going to be in harsh environments, then you adjust the temperature, because some components do have temperature related variances uh, depending on how you set up the simulation. Okay, so for example, resistors, as they heat up, if I recall correctly, they will tend to increase in resistance. Other components will have positive temperature coefficients, so something like a MOSFET. A MOSFET typically what will happen is as temperature increases, the resistance increases, and that limits the flow of current through them, which is actually a good behavior. So it all depends on the circuit that you're working with. But when in doubt, just leave it alone. 90% of the time, it's fine to leave it at 25 degrees C. So in this case, I set up the circuit. This voltage source is going to be putting a sine wave into this circuit. And we're going to see how the circuit behaves. Okay. One thing that we typically recommend with simulation, if you're doing like transient behavior of things that oscillate or that are being subjected to an oscillatory stimulus, is to look for about 5 to 10 cycles. If you have a long time range, what can happen is it can be difficult for the simulation to converge and to give you an actual result. So typically you want to set your start and end time such that maybe you avoid any initial transient startup behavior. And then in that range, you have 5 to 10 cycles. Since I have a 1 kilohertz waveform, every cycle is 1 millisecond. That's why I started at 10 and I ended at 15. In advanced, even though you shouldn't tamper with it most of the time, in advance you have all these parameters that control how the simulator tries to arrive at a solution. So these are convergence parameters. You really don't want to mess with these unless you know exactly what you're doing. One thing that you may have to touch and play with every once in a while is the R shunt. In AC coupled circuits, anything that has capacitors coupling signal, sometimes you have to set R shunt to on. Okay, but that's not the case here, so we're going to leave that alone. So at this point, I'm going to select simulate. And what you're going to see is that we have our different waveforms. And they'll actually, the probes get replaced with these little icons showing you the color of the waveform in the graph. And then you have the current. Now, notice that I didn't explicitly ask for current when I was setting this up. By default, the simulator's been set up in Fusion Electronics to give you the current waveforms of any independent sources. So in our case, we have one independent voltage source. It's showing you how the current changes as the circuit develops. If you're not interested in the current waveform, which many times you're not, you can just turn it off. If you are, then obviously you already have it without having to specify it or adding any type of current probes into the simulation. Okay. So if you look here, we have these two waveforms. Right now they're overlapping. We can go ahead and separate one from the other. That way they can be scaled better. And what you can see is here's our waveform, our sinusoidal waveform that we're inputting. And what you can see is that the waveform ends up cutting the top, which is what we expect. Right on the positive cycle, the LED turns on and it clamps that voltage to the LED forward voltage. So it's behaving as we expect. And then once it goes negative, that LED is no longer clamping the circuit down and you have the full negative waveform. Okay. So this is behaving as expected. So we know that the simulation can be trusted. Now, one thing that sometimes users will do with simulation is that they'll just build up a circuit and simulate it with no expectation of what the results should be. And that is kind of a dangerous road to go down. The idea of simulation is to help you verify the operation of your circuit. So if you have no idea what your circuit is supposed to do, how can you trust that the results shown are accurate? In this case, I had an expectation of what the circuit would do. Once that LED turns on, Vout clamps to whatever the LED's forward voltage is. That's what I'm expecting. And now when I run the simulation, that's what I see. Okay? And you can see it's in phase with the input waveform, which is also an expected behavior. Now, because of the differences in voltages, you'll notice that the waveform looks a little bit different, and that's just because of the voltage scaling here. If I were to put them back together, which I believe I can do, you'll see that now the scaling is the same, and you can see how the waveform operates. And if you notice, whichever one I'm over, that's the symbol that will highlight. So it's really easy to figure out what signal, where the signal is in the circuit, and it can be very helpful. There's a few settings over here that you can set up a logarithmic scale for the x-axis, and that can be useful. The other thing that we have is dark mode. So for those of you maybe that feel more comfortable, it's easier on your eyes, you can just switch it to dark mode. Okay. So this is the first simulation we wanted to show, and obviously it's a very basic simulation, but we wanted to show you how you can map models and set up your own simulations. So I'm going to go ahead and close the simulation, and now we're back here in Fusion 360. So now let's go ahead and show you what this is capable of, some more interesting simulations. So I'm going to go back to my panel over here, and I'm going to pick this 2-transistor oscillator. Okay, expected, downloading, create a view error message. Okay, that's interesting. Was not expecting that. Let me go ahead and save this as a completed example. Okay. All right, let me try to open this one again. Okay, that's fine. Refresh. I bet I know what happened here.
I think is that the electronic document got closed, Jorge, is what I think is going on.
No, because originally I saved it here and then I did a save as. And it looks like it didn't like that I did that. So it's okay. Getting it open now. Oh, awesome. Got a crash.
That's never happened to me.
It's okay. That's the joy of being live. Didn't happen to me earlier when I went through this.
Of course. Always happens when you're live.
It's a good thing. I have a strong computer here at home, so this will be pretty fast. No, I'm not going to cover that. Let's go over here. Let's open this one. There we go. All right, so this is a more interesting circuit. Again, you need to have some expectation of what the circuit is going to do. So this circuit is an oscillator, so it's going to change between two states. Okay. And the way you can understand this one before we even run the simulation so that we all have the same expectation. Okay. Right now, when the circuit gets power, okay, this transistor is going to turn on and current is going to flow through here. It's going to flow through this resistor and it's also going to turn this transistor on. Okay. So as when this transistor turns on, current's going to start to flow. But you notice we have this capacitor right here. Okay. Now a capacitor tries to resist a change in voltage. So initially, both of these nodes are at the same voltage. Okay. But as current flows through here and flows through here, what ends up happening is this current is larger than this one. So this voltage starts to rise, 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 rise. And because the capacitor resists that change, what's going to eventually happen is that this node is going to creep up also. If it creeps up enough, it's going to turn this transistor off. When this transistor turns off, all the current that was going through it now goes through this transistor, and this one gets driven even harder. Okay? So what ends up happening is because now this one is off, there's no current flowing through here, the voltage starts to drop. Okay? Once it drops enough for this transistor to turn on, it will again turn on, robbing current from this one. So now the voltage isn't as high, and then the whole cycle will again repeat. Okay, voltage will again start to rise, eventually cuts this transistor off. Voltage starts to drop here. Once it drops low enough for the transistor to turn back on, then it'll turn back on and drop this one again. So they're basically flipping and flopping between each other. That's what we should expect to see. Okay, so let's go ahead, and this simulation's already been set up. This one is also a transient simulation. Okay, it's ready to go. I hit simulate. There was an issue running this one. Okay. Again, probably broken from before, unable to find the definition of the model. Okay. So let's go ahead and add model to it. Polar junction transistor, map, load the model. Okay. This one is going to be over here. And these files are examples that came with Eagle, and I just moved them over into here. Analog, oscillator. There we go. Say OK. You see here, you see how this model has some additional information. So in this NPN model, all of these attributes have been specified, and that comes from the manufacturer. I'm going to say OK. I contain enough. Yeah, it's okay. Say OK. I do. So it seems something is broken in here. Okay, let's do this. This is how I did it before. Just going to go ahead and do it again. I go over here. Demos. New electronics design. I'm going to go ahead and reference a schematic document. Select from the computer. And GSpice analog. I'm basically linking an existing schematic into this electronics design. What this will do is it'll pull it up into Fusion 360, and then it will basically live in Fusion 360. So I'm going to go over here to oscillator, pick this, hit open. Okay, it's now associated. I'm going to go over here and save it. Actually, before I do that, let me just go ahead and run the simulation so you guys can see it. And there we are. Okay. So what are the key points here? Again, here's current. It kind of hints at what we're expecting, but I'm not really interested in the current. I'm going to turn that off. I'm going to go ahead and separate the V out so we can see it. Okay. So V out is the output of the oscillator. Okay. And you can see it flipping between the two states. Okay. You can see it. It's high, which is a 6 volts, and then it drops to the 4, and then it's constantly switching. It's not the cleanest waveform ever, but for such a simple oscillator, this is actually very usable. Okay, so you can see how this is working. If we look at VCQ2, this is showing the behavior here. And what you notice is that they're in different cycles. They're in antiphase, right? When this one is low, this one is high. Okay? So we can see that. So when this voltage goes high, it's because this transistor is off. Okay? So you see that voltage dropping down to 4, but then slowly coming up. And eventually, once it gets to the right point, you'll see that this now drops because this transistor is on. It's getting current to flow. And when this transistor is on, it's removing current from this one, and you have the high point of the curve. Okay, so this is all what we're expecting. Again, simulation is a verification tool. You shouldn't just throw things in willy-nilly and see what pops out. Okay, because then it's not really helping you. It's not really giving you insight into whether your circuit is going to work, or if maybe there's an assumption that you made that was incorrect. All of those things can be verified and checked if you have an expectation of the output. So that's the key point that we want to emphasize here. When you use simulation, make sure you have some expectation. And again, over here, I can zoom in and I can see where the various measurement points are. Okay. So I'll go ahead and close the simulation window. Now we're back to Fusion 360. And let me go ahead and show you another example. So I'm going to go ahead and save this one. Save. Okay, yeah, now this one's okay here. I'll now open the final simulation example that we wanted to show, which is this one right here. Okay, and this is basically to show what's possible. In this one, we're simulating both analog circuitry and digital circuitry. Okay, and the key point to take away from here is that as far as the simulator is concerned, digital and analog are two separate domains. Okay, in an analog simulation, you can see how the voltage varies continuously as time goes on. In the case of a digital simulation, the only thing you're really interested in are ones and zeros. So in setting these up, you have to use the bridges. Okay, so if we look here, we have a bridge that takes us from the analog domain into the digital domain. Okay, and then similarly, there should be one that goes from digital domain here to analog. So whenever you need to transition domains, you use these bridges in order for the simulation to work. So let's take a look. Now this one's going to have a lot of waveforms. Okay, so let's go ahead and simulate this one. Again, this is a transient one. Hit simulate. Okay, and there's a lot here. Okay, there's a lot of waveforms, a lot to look at. And again, here we can simulate. We can look at what's being measured. Okay, now you're going to notice we have all these currents that in our case we're not interested in, so I'm just going to minimize that. And now we can see the digital results. Okay, so let's start first by understanding what's over here. Okay, first, if we look here, we have this waveform. So we're outputting a square wave, okay, that has what looks to be like a 300 millisecond pulse width, and then it lasts a total of 7 milliseconds, okay? The 1 nanos that are here is basically to indicate that the rise time is really, really fast, so it looks like a square, okay? So that looks good. So far, that's what we're expecting. It goes from 0 to 300 millivolts. It gets amplified by a factor of 10 over here, and that's what's expected. So that's good. That's promising. Okay. Then here in the digital realm, we see that this square wave has been turned into this digital input here. And now we have all these outputs. And what you can see when you look at the digital simulation is that it only shows you ones and zeros. That's all the digital simulation is interested in. And we can look at the different waveforms, what we should expect. Okay, and as you can see here, A out digital, it's identical to the A out from the amplifier. So that's a good sign. It's lining up. That's what we were kind of expecting. So that's a good sign. That implies that we've made this transition from the analog domain into the digital domain correctly. So we're good there. Then here you can see how the different clock inputs, the different signals are used, and they're processed through digital logic to create different results. Okay, so for example, we can check a couple of things here. With the OR output, okay, the OR output, if either Q out or the clock are high, then OR is high. Right? So, and we can actually reorganize these. So I can put this over here, Q out and the clock. Okay. If either of these is high, then the OR should be high, and it is. See? These high, this is low, but this one's still high. Okay, either or, either or. Now this one's high, so that's still high, but now low, and they're both low, so OR is low. So the OR is behaving as we would expect. That part of it's okay. Okay, what about the AND? In the case of the AND, if Q out and the clock, okay, if they're both high, then you have a 1. Otherwise, it's a 0. Okay, so let's check out the AND, and we'll compare. Both are high, we have high. Over here, one is high, one is low, low. Both are high, that's high. One is low, the other, that's low. Here you have kind of a funky transition where it's kind of indeterminate. Okay, so that's something where the simulator couldn't quite handle it very well. Here, because this is low the whole time, this stays low. You can see this. So you can see that this, in a real circuit, this would be a glitch. Okay, because the reality is that there would be probably some time differential here, some delay, and you may not get that glitch of an indeterminate state. But that's something to be aware of. You know, if they're perfectly in time, what happens here? Okay. So overall, the results are looking like what we expect. Now, if we look here, this A out digital from the AND, okay, is getting filtered by a high pass filter. Okay, so it's been converted to digital. Sorry, from digital to analog. And now it's being high passed. Okay. So another way to look at a high pass is as basically as a derivative function. Okay. So what we want to look at when we take this AND waveform, okay, we want to compare it to what the AND filter is showing us. Okay. So we're going to go ahead and grab over here the AND function. Whoops, I did not mean to zoom in like that. There we go, I've reset it. And you can see that it kind of lines up, okay? So it's behaving how we would expect. You get the weird transition here, and then you have this delay in getting back to the waveform. So everything is kind of what we expect, okay? So that's the key thing we want to take away again. You need to have some idea of what you're expecting out of this circuit, okay? So that's the thing we want to keep in mind here, okay? That we want to know what we're expecting to see, and then the simulator should confirm that. Okay, so that's what we wanted to show you today.
Yeah, we wanted to cover all three of them, which is basically analog, digital, and mix. And very well explained, Jorge. Thank you very much. Appreciate that.
Okay, do we have any questions in the in the YouTube chat? I'm sure we do.
So far we're okay on the YouTube. I think it got pretty packed. It is pretty packed. So I'm just gonna go ahead and add our one having join.
You're breaking up on me, Ed.
So and get ready for joining us. This covers all the material that we wanted to cover for today's.
Ed, you still there? Ed? Ed? Ed, you there? Ed? Looks like Ed dropped off. So thank you everyone for joining us on this webinar. We really appreciate the time. If you guys have any questions, Ed will have put into the chat on YouTube the support address. So please feel free to reach out if you have any additional questions on the subject, and we look forward to our next webinar. Thank you everyone for joining us. And again, we welcome any feedback, any comments in the video. Thank you very much. Have a great day.